Hello, hi. Today we are going to discuss about the A-star search algorithm for graph traversal. The motivation for this graph traversal algorithm came from the need to make intelligent mobile robots which can do tasks on their own and which need not be commanded at every time step about what to do next. So this was first developed as a part of the Shaky project where the roboticists aimed to develop a robot which can detect a block on the table, travel towards it uh, by avoiding obstacles and climbing on steps, and to tip it over the table. So, for doing this task precisely, the robot had to make many decisions, such as what is the height of the step, where is the block exactly located on the table, how to move towards the block, and at what angle do we need to does it need to apply a force to tip the block over the table? For these decision-making processes, it used a A-star search algorithm to make decisions and to move from one pose to the other. So the main idea here is to move from a start to end pose in a weighted graph in a manner such that it minimizes the total cost to move from the start to the end pose. So this algorithm is formulated in a best first way where it uh, minimizes the minimizes the local cost first, and then it iterates over all the nodes to get the global minimum of the graph edge weights. So this is a heuristic approach which maintains a tree of paths where each node has a value assigned to it, where GZ is the value to travel from the start node to that particular node, and HZ is a heuristic value which is updated at every time step and initialized to a particular value initially. And we calculate this for every node, and and then determine what is the minimum weighted path to go from the start to the end. So here is a worked out example which shows how to go from S, which is the start pose, to the end pose. So we have the initialized values for H, and so suppose for A we have from A to E it is 7 plus 3 is 10, but heuristic value is 5. So we always assign a value which is less than the cost, which is 7 plus 3 is 10. So we assign a value here which is less than 10. So we assign it here 5. We can assign it anything below 10. So if we start from S and we expand from A to A and B, so here the cost is 1. 1 plus the heuristic value is 5. So 1 plus 5 is 6. Similarly for B, it is 8. So here we get the minimum value is from S to A. So we expand A and we retain this S to B. So when we expand A, we can either go to X or to Y. So if we go to X, similarly it gives us 10 and 16. So here the minimum is S to B, so we expand B again. So from B we can go to C and D and retain this SAX and SAY. So when we go to S, from S to B to C, we get the cost is 13, and from S to B to D is 18. So minimum here is S to A to X is 10. And hence, then from X, we again expand this particular set and we get E, and the cost is 7. So this is a basic algorithm for a very simple graph. This can be expanded to other complex graph algorithms. So graph data structures, pardon. So graph data structures. So here we see a complete algorithm where we initialize the A star search. The closed list is a list of all the visited nodes, and open list is the node where we are currently. So if the open list is empty, then it means that there's no node in the graph, so there is no solution. If n is the heuristically best node, so we initialize the n to be the heuristically best node, and if it is the final node, then we return the path from start to the goal node. But if it is not the final node, then we for this heuristically best node we look for all the directly available nodes, and if the directly available nodes are not in the open or in the closed list, we calculate the heuristics for them, and then we assign the current node as its parent node. Also, if that particular node is in the closed list but not in the open list, then we check the path from the start node to the current node. And if it is better than all the other paths which we found out in the previous step, then we transfer that particular node from the current node, that particular node from the closed list to the open list, and set n as its parent node. After doing all this, as we have already searched this particular node, so we transfer it from the open list to the closed list. So, and this we do for every particular node until we get till the end. So this is what the algorithm is, and hopefully you enjoyed the video.